Good morning. Today we will discuss about how to estimate the fundamental component, the phasor of the fundamental components. In the last lectures, we have seen how to determine the Walsh coefficients and also Walsh functions. We have seen the development of basic algorithm and applying the basic algorithm for determining the Walsh functions. Then we have also seen how to determine the Walsh coefficients for discrete data which is available for us. So in today's class, we will apply this developed Walsh functions and determine the Walsh coefficients for extracting the phasor of fundamental components. So I'll start with the basic contents. So digital relay using Walsh functions was developed originally to reduce the burden on computers. So just by adding and shifting operations in fixed point format. So to reduce the burden of multiplying, dividing, squaring and square rooting. So all these operations were reduced with the help of these Walsh functions when compared to Fourier coefficients. You know that we have already seen that Walsh functions, they generally take the values of either +1 or -1. And they do have a sequency which is number of the polarity changes in a time period. And also, there are two methods for estimating the fundamental components using Walsh coefficients. And these two methods are, for the first one is the indirect method and the direct method. So in your syllabus, there is only qualitative treatment of these two methods. So I'll just explain these two methods which were proposed by the researchers. The first one is an indirect method wherein you will be determining the amplitude and phase angle of the fundamental components using Walsh coefficients, and then you transform them into Fourier coefficients using Walsh Fourier transformation matrix. This we have already seen. It is represented by A. So first of all, you will be computing W and then you will be computing A. With the help of these two, you will be computing the Fourier coefficients. So if these represent the Walsh coefficients of a voltage signal, where k is varying from 0 to infinity, using these coefficients, it is possible to estimate the Fourier coefficients, right? So normally, if you do have a 10 by 10 A matrix, which is a standardized one, you know that A matrix, F is equal to A inverse into W, right? So if I do have this A matrix, 10 by 10 A matrix, so these, and if I do have different Walsh coefficients also, let us suppose from W1 to W10, if I do have all Walsh coefficients, and if these are standard values, right? A values. So F1 to F10, it can be obtained in terms of, you can go with F0 also, right? So the fundamental component F1 is basically given by, these are the Walsh coefficients, if you carefully see, for k is equal to 1, k is equal to 5 and k is equal to 9, right? So these values, A matrix values, which we have computed in the last class, these are the terms of A matrix. Similarly, the second component also, it can be computed using these even coefficients. Once you do have these Fourier coefficients of F1 and F2, then automatically you can determine the magnitude of the fundamental component, right? So the formula is V is equal to square root of F1. Magnitude of voltage signal is equal to square root of F1 square plus F2 square. This is root 2 F1 square plus root 2 F2 square. Okay. Similarly, the angle of voltage signal is equal to tan inverse of F2 by F1, where F1 and F2 are the Fourier coefficients of the faulted voltage signal. Similarly, you can go with the current also. Once you do have the current, then you can determine Z. So this is the procedure. So first determine the Walsh coefficients, then determine the A coefficients. A coefficients are generally standard signals. So once you do have the Walsh coefficients, you can calculate F1 and F2. Right, using the formula. F1 requires only W1 W5 and W9. Whereas F2 requires W2, this is W6 and W10. Right, this is what W1. F1 is dependent on W1, W5 and W9, whereas F2 dependent on W2, W6 and W2. Once you have these coefficients, you can determine the fundamental component phasor. Whereas a direct method which was proposed by Horton, they have published this particular direct method in this particular work. So it depends upon two theorems and it gives approximate results. So what they have said is, the first theorem, they have proposed this one based on two theorems. In the first theorem, they have stated that the maximum value of a sinusoid and its time of occurrence can be estimated in terms of first and second Walsh coefficients for the sinusoid. So based upon that, if there is any signal g of t and it is a sinusoidal signal and it is divided into, let us suppose, n number of cycles. So let us suppose n is equal to 60 subintervals. So delta t is equal to t by 60. If this g of signal, g of t, if it is expressed in terms of Walsh coefficients, so this is the representation, right? So if I take to an accuracy of plus or minus 4.28%, the maximum value of this particular signal, it can be obtained just only the first two Walsh coefficients, W1 and W2, using this particular formula. This was the proposal. This was the proposed by the scientist. And the second one was the accuracy for estimating the amplitude of the sinusoid and its time of occurrence can both be improved if all Walsh functions, 16 Walsh functions, are taken into account. But it is a time-consuming process. So if I assume that it is a pure sinusoidal wave with interval t and is divided into 16 subintervals, so this is the representation. So for this one, to an accuracy of, in the earlier case we have seen plus or minus 4.28% accuracy, right? So if you want to improve that accuracy to plus or minus 2.6%, then this is the formula, complex formula a little bit. This is what you are supposed to employ. Where W1 and W2, they do represent this Walsh coefficients, whereas this delta, alpha, gamma and beta, they are given by this. So this is one mechanism. It gives us an accuracy of plus or minus 2.6%. So this can be employed to determine the fundamental component phasor. Now if you do have a pure sinusoidal term, pure sinusoidal wave without any harmonics, so then it's very easier, then you can directly employ the Walsh coefficients. So for that one, how to determine the Walsh coefficients? See, normally let us suppose if I already determined W1, W2, W3 up to W10, and from this I have already determined F1 and F2. See, the other terms might not be present here. These terms may not be present. In this case, because it is a pure sinusoidal one. So in that case, if I want the truly effective Walsh coefficients, W11 and W12, which are related to this one. So in that case, a rough estimation is, this is the rough estimation. So in that case, you know what is already F1. We have already seen F1. What is F1? It depends upon W1, W5 and also W9. F2 depends upon W2, W6 and W12. If I substitute this, this is my expression. These are the generalized Walsh coefficients and these are the two Walsh coefficients of the pure sinusoidal wave. Right? So I hope that now you are able to determine the fundamental component phasor using either purely Walsh coefficients or using Fourier Walsh transformation. You can employ this relation between Fourier and Walsh series, and from that you can determine the fundamental component phasor. So we'll discuss more in the class today. Thank you.